Today's day two of my challenge day. Let's start studying. So in a few days, I learned computation graph, which to compute equation using some kind of steps. Uh, in other words, it divide computation into several steps like this using the variable u and v and j. And in the opposite direction, we do a back propagation to calculate derivatives of final output as intermediate quantities. Mm. This is an example of logistic regression using computation graph. So based on the parameter x1, w1, x2, w2b, we can get a jet, and we put the jet in the sigmoid function, and finally we can calculate the loss function of logistic regression. In the opposite direction, we can calculate the derivatives of loss function using as a final output of dA. So this is the process of computation for one training example. But actually, we need to handle M training example in the real case. So that's why we use those sigma signature in this equation. And using follow the professor's derivation, we can follow these steps to get dB, dw2, dw1, and dz and other required values. You can see there is some kind of duplicated uh, computation when we compute dw1 and dw2. This the right term is exactly same way because so this makes a for loop in general, and it makes our application slow. So that's why it's the vectorization technique comes in handy. For example, let's assume that there is a this kind of a iteration, and if we if you take a traditional approach like for loop, we need uh, to compute a dot product of this equation here W transpose and dot product X, we need to multiply each of element, each of components of W and X in loop. But if you use a numpy library, we can just do this. We can compute this equation in the semantic way. So the reason the numpy library is faster than a traditional loop because they use a seamed instruction. Oh, there's a redundancy. So they can use a GPU and CPU can use a single instruction multiple data. So it's basically we can take advantage of parallelism using the seamed kind of operations. This library is quite optimized for this kind of mathematical computation. So the conclusion is that it is better to vectorize some of the data whenever we can. So I think it's enough to recap myself. Let's start today's.
So you will remember that for the gradient computation, what we did was previous video, you saw how you can use vectorization to compute the predictions, the lowercase a's, for an entire training set all sort of at the same time. In this video, you see how you can use vectorization to also perform the gradient computations for all m training examples, again, all sort of at the same time. And then at the end of this video, we'll pull it all together and show how you can derive a very efficient implementation of logistic regression. So you will remember that for the gradient computation, what we did was we computed DC1 for the first example, which would be A1 plus Y1, and then DC2 equals A2 minus Y2, and so on. So and so on for all m training examples. So what we're going to do is define a variable d capital Z is going to be dz1, dz2, right, dcm. Again, all the d lowercase z variables stacked horizontally, so this will be a 1 by m matrix, or alternatively a m-dimensional row vector. Now recall that from the previous slide, we'd already figured out how to compute capital A, which was this A1 through AM. And we had defined capital Y as Y1 through YM, also, stacked horizontally. So based on these definitions, maybe you could see for yourself that dz can be computed as just A minus Y, because this is going to be equal to A1 minus Y1, that's going to be the first element, A2 minus Y2, that's going to be the second element, and so on. So this first element, A1 minus Y1, is exactly the definition of DC1. The second element is exactly the definition of DC2. and so on. So with just one line of code, you can compute all of this at the same time. Now, in the previous implementation, we gotten rid of one for loop already, but we still had this um, second for loop over training examples. So we initialized dw to 0, to the vector of zeros, but then we still had to loop over training examples where we have dw plus equals x1 times dz1 for the first training example, dw plus equals x2, dz2, and so on. So we do the m times, and then dw divide equals by m. And similarly for b, right? db was initialized as 0, and db plus equals dz1, db plus equals dz2, down to, dz_m, and then db divided equals m. So that's what we had in the previous implementation. We'd already gotten rid of one for loop, so at least now dw is a vector, and we weren't separately updating dw1, dw2, and so on. So we gotten rid of that already, but we still had a for loop over the m examples in the training set. So let's take these operations and vectorize them. Here's what we could do. For the vectorized implementation of db, what it's doing is basically summing up all of these dz's and then dividing by m. So dp is basically 1 over m, sum from I equals 1 through m of dci, and well, all the dz's are in that row vector. And so in Python, what you do is implement 1 over m times np dot sum of dc, right? So just take this variable and call the np dot sum function on it, and that will give you dp. Huh? W. Or just write out the correct equation to verify is the right thing to do. dW turns out to be 1 over m times the matrix X times dc transpose. And to kind of see why that's the case, this is equal to 1 over m. Then the matrix X is x1 through xm, right? Stacked up in columns like that. And dz transpose would be dz1 down to dcm, like so. And so if you figure out what this matrix times this vector works out to be, this turns out to be 1 over m times x1 dz1 plus dot 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 plus xm dcm, right? And so this is a n by 1 vector, and this is what you actually end up with dw, because dw was taking these, xi, dzi and adding them up. And so that's what exactly this matrix vector multiplication is doing. And so again, with one line of code, you can compute dw. So the vectorized implementation of the derivative calculations is just this. Use this line to implement dp, and use this line to implement dw. And notice that without a for loop over the training set, you can now compute the updates you want to. So now let's put it all together into how you would actually implement logistic regression. So this is our original highly inefficient non-vectorized implementation where so the first thing we done in the previous video was get rid of this form, right? So instead of looping over dw1, dw2, and so on, we have replaced this with a vector value dw. Just say this is dw plus equals xi, which is now a vector, times dci. But now we'll see that we could also get rid of not just the for loop below, but also get rid of this for loop. So here's how you do it. So using what we had from the previous slides, you would say capital Z is equal to W transpose X plus B, and the code you write is capital Z equals NP dot W transpose X plus B, and then A equals sigmoid of capital Z. So you've now computed all of this and all of this for all the values of I. Next, on the previous line, we said you would compute dz equals capital A minus capital Y. So now you computed all of this for all the values of I. Then finally, dw equals 1 over m x z transpose, and dp equals 1 over m of, np dot sum dz. So you've just done forward propagation and back propagation, really computing the predictions and computing the derivatives on all m training examples without using a for loop. And so the gradient descent update then would be, W gets updated as W minus the learning rate times dW, which we just computed above, and B gets updated as B minus the learning rate times dB. Because sometimes it's putting colons there to denote this is up assignment. But I guess I haven't been totally consistent to that notation. But with this, you've just implemented a single iteration of gradient descent for logistic regression. Now, I know I said that we should get rid of explicit for loops whenever you can, but if you want to implement um, multiple iterations of gradient descent, then you still need a for loop over the number of iterations. So if you want to have 1,000 iterations of gradient descent, you might still need a for loop over the iteration number. There's an ultimos for loop like that. And I don't think there's any way to get rid of that for loop. But I do think it's incredibly cool that you can implement at least one iteration of gradient descent without needing to use a for loop. So that's it. You now have a highly vectorized and highly efficient implementation of gradient descent for logistic regression. There's just one more detail that I want to talk about in the next video, which is in our description here, I briefly alluded to this technique called broadcasting. Broadcasting turns out to be a technique that Python and NumPy allows you to use to make certain parts of your code also much more efficient. So let's see some more details of broadcasting in the next video. Previous video, I mentioned that broadcasting is another technique that you can use to make your Python code run faster. In this video, let's delve into how broadcasting in Python actually works. Let's motivate broadcasting with an example. In this matrix, I've shown the number of calories from carbohydrates, proteins, and fats in 100 grams of 4 different foods. So for example, 100 grams of apples turns out has 56 calories from carbs and much less from proteins and fats. Whereas in contrast, 100 grams of beef has 104 calories from protein, 135 calories from fat. Now, let's say your goal is to calculate the percentage of calories from carbs, proteins, and fats for each of the 4 foods. So, for example, if you look at this column and put up the numbers in that column, you get that 100 grams of apple is 56 plus 1.2 plus 1.8. So that's 59 calories. And so, as a percentage, the percentage of calories from carbohydrates in an apple would be 56 over 59, that's about 94.9%. So most of the calories in an apple come from carbs, whereas in contrast, most of the calories of beef come from protein and fat, and so on. So the calculation you want is really to sum up each of the 4 columns of this matrix to get the total number of calories in 100 grams of apple, beef, eggs, or potatoes, and then to divide throughout the matrix um, so as to get the percentage of calories from carbs, proteins, and fats for each of the 4 foods. So the question is, can you do this without an explicit for loop?
Some each column, each class, each average.
Let's take a look at how you could do that. What I'm going to do is show you how you can set, say, this matrix equal to a 3 by 4 matrix A. And then with one line of Python code, we're going to sum down the four numbers corresponding to the total number of calories in these four different types of food, 100 grams of these four different types of food. And I'm going to use a second line of Python code to divide each of the four columns by their corresponding sum. If that verbal description wasn't very clear, hopefully it'll be clearer in a second when we look at the Python code. So here we are in the Jupyter notebook. I've already written this first piece of code to pre-populate the matrix A with the numbers we had just now. So hit Shift Enter, just run that. So there's the matrix A. And now here are the two lines of Python code. First, I'm going to compute cal equals A dot sum, and axis equals 0 is the sum vertically. Say more about that a little bit. And then let's print cal. So with sum vertically, so as we say just now, 59 is the total number of calories in the apple. 239 was the total number of calories in the beef, and the eggs, the potato, and so on. And then with the compute percentage equals A over cal dot reshape 1 by 4. Actually, we want percentages multiplied by 100 here. And then let's print percentage. Let's run that. And so that command, we've taken the matrix A and divided it by this 1 by 4 matrix. And this gives us the matrix of percentages. So as we worked out kind of by hand just now, in the apple, that was the first column, 94.9% of the calories of columns. Let's go back to the slides. So just to repeat the two lines of code we had, this is what we had written out in the Jupyter notebook. To add a bit of detail, this parameter axis equals 0 means that you want Python to sum vertically. So this is axis 0, it's the sum vertically, whereas the horizontal axis is axis 1. So if it's right axis 1, will sum horizontally to sum vertically. And then this command here, this is an example of Python broadcasting where you take a matrix A. So this is a 3 by 4 matrix, and you divide it by a 1 by 4 matrix. And technically, after this first line of code, cal, the variable cal, is already a 1 by 4 matrix. So technically, you don't need to call reshape here again. So that's actually a little bit redundant. But when I'm writing Python codes, if I'm not entirely sure what matrix, what are the dimensions of that matrix, I often would just call a reshape command just to make sure that is the right column vector or the row vector or whatever you want it to be. The reshape command is a constant time, it's an order 1 operation, so it's very cheap to call. So don't be shy about using the reshape command to make sure that your matrices are the size you need it to be. Now, let's explain in greater detail how this type of operation works, right? We had a 3 by 4 matrix and we divided it by a 1 by 4 matrix. So how can you divide a 3 by 4 matrix by a 1 by 4 matrix, or by a 1 by 4 vector? Let's go through a few more examples of broadcasting. If you take a 4 by 1 vector and add it to a number, what Python will do is take this number and auto-expand it into a 4 by 1 vector as well, as follows. And so the vector 1, 2, 3, 4 plus the number 100 ends up with that vector on the right. You're adding 100 to every element. And in fact, we used this form of broadcasting where that constant was the parameter b in an earlier video. And this type of broadcasting works with both column vectors and row vectors. And in fact, we used a similar form of broadcasting earlier with the constant we're adding to a vector being the parameter b in logistic regression. Here's another example. Let's say you have a 2 by 3 matrix and you add it to this 1 by n matrix. So the general case would be if you have some m by n matrix here and you add it to a 1 by n matrix. What Python will do is copy the matrix m times to turn this into an m by n matrix. So instead of this 1 by 3 matrix, I'll copy it twice in this example to turn it into this also 2 by 3 matrix. and they'll add these, so you end up with this sum on the right. Okay, so you've taken, you added 100 to the first column, added 200 to the second column, added 300 to the third column. And this is basically what we did on the previous slide, except that we use a division operation instead of an addition operation. Just one last example. What if you have a m by n matrix and you add this to an m by 1 vector, an m by 1 matrix? Then this will copy this n times horizontally, so you end up with an m by n matrix. So as you can imagine, you'll copy it horizontally 3 times and add those. So when you add them, you end up with this. So we've added 100 to the first row and added 200 to the second row. Here's the more general principle of broadcasting in Python. If you have an m by n matrix, and you add or subtract or multiply or divide with a 1 by n matrix, then this will copy it m times into an addition, subtraction, multiplication, or division element-wise. If conversely, you were to take the m by n matrix and add, subtract, multiply, divide by m by 1 matrix, then also this would copy it now n times and turn that into an m by n matrix and then apply the operation element-wise. Just one other form of broadcasting, which is if you have an m by 1 matrix, so that's really a column vector, like 1, 2, 3, and you add, subtract, multiply, or divide by a real number. So maybe you have 1 by 1 matrix, so such that plus 100, then you end up copying this real number n times until you also get another n by 1 matrix, and then you perform the operation, such as addition in this example, element-wise. And something similar also works for row vectors. The fully general version of broadcasting can do even a little bit more than this. If you're interested, you can read the documentation for numpy and look up broadcasting in that documentation. That gives an even slightly more general definition of broadcasting. But the ones on this slide are the main forms of broadcasting that you end up needing to use when you implement a new network. Before we wrap up, just one last comment, which is for those of you that are used to programming in either MATLAB or Octave, if you've ever used the MATLAB or Octave function bsxfun in neural network programming, bsxfun does something similar, not quite the same, but is often used for a similar purpose as what we use broadcasting in Python for. But this is really only for very advanced MATLAB and Octave users. If you've not heard of this, don't worry about it. You don't need to know it when you're coding up neural networks in Python. So that was broadcasting in Python. I hope that when you do the programming homeworks, that broadcasting will allow you to not only make your code run faster, but also help you get what you want done with fewer lines of code. Before you dive into the programming exercise, I want to share with you just one more set of ideas, which is that there's some tips and tricks that I found reduces the number of bugs in my Python code, and that I hope will help you too. So with that, let's talk about that in the next. Video. The ability of Python to allow you to use broadcasting operations, and more generally, the great flexibility of the Python NumPy programming language is, I think, both a strength as well as a weakness of the programming language. I think as a strength, generally, the ability of Python to allow you to use broadcasting operations, and more generally, the great flexibility of the Python NumPy programming language is, I think, both a strength as well as a weakness of the programming language. I think it's a strength because the great expressivity of the language, the great flexibility of the language lets you get a lot done, with even just a single line. But there's also weakness because with broadcasting and this great amount of flexibility, sometimes it's possible you can introduce very subtle bugs or very strange looking bugs if you aren't familiar with all of the intricacies of how broadcasting and how features like broadcasting work. For example, if you take a column vector and add it to a row vector, you would expect it to throw up a dimension mismatch or type error or something. But you might actually get back a matrix as a sum of a row vector and a column vector. So there is an internal logic to these strange effects of Python, but if you're not familiar with Python, then I've seen some students have very strange, very hard to find bugs. So what I want to do in this video is share with you a couple of tips and tricks that have been very useful for me to eliminate or simplify and eliminate a lot of the strange looking bugs in the code. I hope that with these tips and tricks, you also be able to much more easily write bug-free Python and NumPy code. To illustrate one of the less intuitive effects of Python NumPy, especially how you construct vectors in Python NumPy, let me do a quick demo. Let's say I set A equals np.random dot rand n 5. So this creates a five random Gaussian variables stored in an array A. And so let's print A. And now it turns out that the shape of A when you do this is this five column um, structure. And so this is called a rank one array in Python, and it's neither a row vector nor a column vector. And this leads it to have some slightly non-intuitive effects. So for example, if I print A transpose, it ends up looking the same as A. So A and A transpose end up looking the same. And if I print the inner product between A and A transpose, you might think A times A transpose is maybe the outer product, should give you a matrix maybe. But if I do that, you instead um, get back a number. So what I would recommend is that when you're coding neural networks, that you just not use data structures where the shape is this, 5 comma or n comma rank one array. Instead, if you set A to be this 5 by 1, then this commits A to be a 5 by 1 column vector. And whereas previously A and A transpose look the same, if you now print A transpose, now A transpose is a row vector. Notice one subtle difference. In this data structure, there are two square brackets when you print A transpose, whereas previously there was one square bracket. So that's the difference between this is really a 1 by 5 matrix versus a one of these are rank one arrays. And if you print, say, the product between A and A transpose, then this gives you the outer product of a vector, right? So the outer product of a vector gives you a matrix. So let's look in greater detail at what we just saw here. The first command that we ran just now was this, and this created a data structure where A dot shape was this funny thing 5 comma. And so this is called a rank one array. And this is a very funny data structure. It doesn't behave consistently as either a row vector nor a column vector, which makes some of its effects non-intuitive. So what I'm going to recommend is that when you're doing your programming exercises, or in fact when you're implementing logistic regression on your networks, that you just do not use these rank one arrays. Instead, if every time you create an array, you commit to making it either a column vector, so this creates a either one vector or commit to making it a row vector, then the behavior of your vectors will make it easier to understand. So in this case, a dot shape is going to be equal to 5 comma 1. And so this behaves a lot like that this is a column vector. And that's why you can think of this as a 5 by 1 matrix, or as a column vector. And here, a dot shape is going to be 1 comma 5, and this behaves consistently as a row vector. So when you need a vector, I would say either use this or this, but not a rank 1 array. One more thing that I do a lot in my code is if I'm not sure what's the dimension of one of my vectors, I'll often throw in an assertion statement like this to make sure in this case that this is a 5 by 1 vector, so it's a column vector. These assertions are really inexpensive to execute, and they also help to serve as documentation for your code. So don't hesitate to throw in assertion statements like this whenever you feel like it. And then finally, if for some reason you do end up with a rank 1 array, you can reshape this, A equals A dot reshape, into, um, say, a 5 by 1 array or a 1 by 5 arrays. As either a column vector or a row vector. So I've sometimes seen students end up with very hard to track down bugs because of some of the non-intuitive effects that rank 1 arrays. By eliminating rank 1 arrays on my own code, I think my code became simpler, and I did not actually find it restrictive in terms of things I could express in code to just never use a rank 1 array. And so takeaways are to simplify your code, don't use rank 1 arrays. Always use either n by 1 matrices, basically column vectors, or 1 by n matrices, or basically row vectors. Feel free to toss a lot of assertion statements to double check the dimensions of your matrices and arrays. And also, don't be shy about calling the reshape operation to make sure that your matrices or your vectors are the dimension that you need it to be. So that I hope that this set of suggestions helps you to eliminate a class of bugs that from Python code and makes the programming exercise easy for you to complete.
Mm.
With everything you've learned, you're just about ready to tackle your first programming assignment. Before you do that, let me just give you a quick tour of IPython notebooks in Coursera. Here's the Jupyter IPython notebook that you can get to on Coursera. Let me just quickly show you a few features of this. The instructions are written right here in the text in the IPython notebook, and these long, light gray blocks are blocks of code. So occasionally you see in these blocks something that looks like this. There's start code here and end code here. To do the programming exercise, please make sure to write your code between the start code here and end code here. So, for example, print hello world, right? And then to execute a code block, you can hit Shift Enter, and then to execute this code block, which I guess we just wrote print hello world, so that printed hello world. To run a cell, you can also, to run one of these code blocks in cell, you can also click cell and then run cell, so that executes this. Um, it's possible that on your computer, the keyboard shortcut for cell run cell might be different than Shift Enter, but it's on both my Mac as well as on my PC is Shift Enter, so it might be the same for you as well. Now, when you're reading the instructions, if you accidentally double click on it, you will end up with this markdown language. If you end up with this funny looking text, to convert it back to the nice looking text, just run this cell. So you can go to cell, run cell, or I'm going to hit Shift Enter, and that basically executes the markdown and turns it back into this nice looking code. Just a couple more tips. When you execute code like this, it actually runs on a kernel, on a piece of code that runs on the server. Um, if if you're running an excessively large job, or if you leave a computer for a very long time, or something goes wrong with your internet connection or something, there is a small chance that the kernel on the back end might die. In which case, just click kernel and then restart kernel, and hopefully that will reboot the kernel and make it work again. So that shouldn't happen if you're just running relatively small jobs and you just started up the IPython notebook. But if you see an error message that the kernel has died or something, you can try kernel restart. Finally, in an IPython notebook like this, there may be multiple blocks of code. So even if an earlier block of code doesn't have any created code, be sure to execute this block of code, because in this example, it imports numpy as np and so on, and sets up some of the variables that you might need in order to execute the lower down blocks of code. So be sure to execute the ones on top, even if you aren't asked to write any code from them. And finally, when you're done implementing your solutions, there's this blue submit assignment button here on the upper right, and we click that and we'll submit your solutions for grading. I found that the interactive command shell nature of IPython notebooks to be very useful for letting you quickly implement a few lines of code, see an outcome, learn and iterate quickly. And so I hope that the programming exercises in the Coursera Jupyter IPython notebooks will help you quickly learn and experiment and see how to implement these learning algorithms. There's one more video after this optional video that talks about the cost function for logistic regression. You can watch that or not, either way is perfectly fine. But either way, best of luck with the week 2 programming assignment, and I also look forward to seeing you at the start of the week 3 materials. Earlier video, I've written down the form for the cost function for logistic regression. In this optional video, I want to give you a quick justification for why we like to use that cost function for logistic regression. To quickly recap, in logistic regression, we have that the prediction y hat is sigmoid of w transpose x plus b, whereas sigmoid is this familiar function. And we said that we want to interpret y hat as the probability that y is equal to 1 given x. So we want our algorithm to output y hat as the chance that y is equal to 1 for a given set of input features x. So another way to say this is that if y is equal to 1, then the chance of y given x is equal to y hat. And conversely, if y is equal to 0, then the chance that y was 0 was 1 minus y hat, right? So if y hat was a chance that y is equal to 1, then 1 minus y hat is a chance that y is equal to 0. So let me take these last two equations and just copy them to the next slide. So what I'm going to do is take these two equations, which basically define p of y given x, for the two cases of y equals 0 or y equals 1. And I'm going to take these two equations and summarize them into a single equation. See, define 0. So let me take these long equations and just copy them to the next slide. So what I'm going to do is take these two equations, which basically define t of y given x, for the two cases of y equals 0 or y equals 1. And I'm going to take these two equations and summarize them into a single equation. I just want to point out y has to be either 0 or 1 because we're in binary classification, so y equals 0 or 1 are the only two possible cases, right? Let someone take these equations and summarize them as follows. Let me just write out what it looks like, then we'll explain why it looks like that. So minus y hat to the power of 1 minus y. So it turns out this one line summarizes the two equations on top. Let me explain why. So in the first case, suppose y is equal to 1, right? So if y is equal to 1, then this term ends up being y hat because that's y hat to the power of 1. This term ends up being 1 minus y hat to the power of 1 minus 1, so that's the power of 0. But anything to the power of 0 is equal to 1. So that goes away. And so this equation just says p of y given x equals y hat when y is equal to 1. So, that's exactly what we wanted. Now, how about the second case? What if y equals 0? If y is equal to 0, then this equation above is p of y given x equals y hat. Zero, but anything to the power of 0 is equal to 1. So that's just equal to 1 times 1 minus y hat to the power of 1 minus y. So 1 minus y is 1 minus 0, so this is just 1. And so this is equal to 1 times 1 minus y hat, which is just equal to 1 minus y hat. And so here we have that y equals 0, p of y given x is equal to 1 minus y hat, which is exactly what we wanted above. So what we've just shown is that this equation is a correct definition for p of y given x. Now, finally, because the log function is a strictly monotonically increasing function, maximizing log of p of y given x should give you um, a similar result as optimizing p of y given x. And if you compute log of p of y given x, that's equal to log of y hat to the power of y, 1 minus y hat to the power of 1 minus y. And so that simplifies to um, y log y hat plus minus. What we've just shown is that this equation is a correct definition for p of y given x. Now, finally, because the log function is a strictly monotonically increasing function, maximizing log of p of y given x should give you
Strictly monotonically.
finally, um, because the log function is a strictly monotonically increasing function, maximizing log of p of y given x should give you um, a similar result as optimizing p of y given x. The log of p of y given x, that's equals to log of y hat to the power of y, 1 minus y hat to the power of 1 minus y. And so that simplifies to um, y log y hat plus 1 minus y times log 1 minus y hat, right? And so this is actually negative of the loss function that we had. It's a negative sign there because usually if you're training a learning algorithm, you want to make probabilities large, whereas in logistic regression, we're expressing this, we want to minimize the loss function. So minimizing the loss corresponds to maximizing the log of the probability. So this is what the loss function on a single example looks like. How about the cost function, the overall cost function on the entire training set on M examples? Let's figure that out. So the probability of all the labels in the training set, right, writing this out a little bit informally, is if you assume that the training example are drawn independently or drawn IID, identically independently distributed, then the probability of the examples is product of probabilities. Product from I equals 1 through m of p of yi given xi. And so if you want to carry out maximum likelihood estimation, right, then you want to maximize the find the parameters that maximizes the chance of your observations in training set. But maximizing this is the same as maximizing the log, so we should put logs on both sides. So log of the probability of the labels in the training set is equal to log of a product is the sum of a log, so the sum of y equals 1 through m of log p of y I given xi. And we had previously figured out on the previous slide that this is negative L of y hat I, yi. And so in statistics, there's a principle called the principle of maximum likelihood estimation, which just means to choose the parameters that maximizes this thing, or in other words, that maximizes, this thing, right? Negative sum from y equals 1 through m, L of y hat I, yi. I just moved the negative sign outside the summation. So this justifies the cost we had for logistic regression, which was J of WP of um, this. And because we now want to negative observations in training set, the examples is product of probability wants to maximizing the log of the probability. So this is what the loss function on a single example looks like. How about the cost function, the overall cost function on the entire training set on M examples? Let's figure that out. So the probability of all the labels in the training set so a little bit informally is if you assume that the training examples are drawn independently or drawn IID, identically independently distributed, then the probability of the examples is product of probabilities. Through m p of yi given xi. And so if you want to carry out maximum likelihood estimation, right, then you want to maximize the find the parameters that maximizes the chance of your that but maximizing this is the same as want to maximize I given xi. And so if you want to carry out maximum likelihood estimation, maximize the find the parameters that maximizes the chance of your observations and training set. But maximizing this is the same as maximizing the logs, split logs on both sides. So log of the probability of the labels in a training set is equal to log of a product is the sum of a log. So the sum from y equals 1 is m of log p of y I given xi. And we had previously figured out on the previous slide that this is negative L of y at I, yi. And so in statistics, there's a principle called the principle of maximum likelihood estimation, which just means to choose the parameters that maximizes this thing, or in other words, that maximizes, this thing, right? Negative sum from y equals 1 through m, L of y hat I, yi. I just move the negative sign outside the summation. So this justifies the cost we had for logistic regression, which was J of WP of this. But, because we now want to minimize the cost instead of maximize the likelihood, we've gotten rid of the minus sign. And then finally, for convenience, so to make sure that our quantities are better scaled, we just add a 1 over m extra scaling factor there. But so to summarize, by minimizing this cost function J of WP, we're really carrying out maximum likelihood estimation with the logistic regression model under the assumption that our training examples were IID or identically and independently distributed. So thank you for watching this video, even though this is optional. I hope this gives you a sense of why we use the cost function we do for logistic regression. And with that, I hope you go on to the exercises, the problem exercise and the quiz questions for this week. Best of luck with both the quizzes and the referring.
The laws correspond with mathematical to the P or S. True. Okay, I'm gonna end up today's recording after a recap. What did I learn today? So I've started the vectorization problem. Mm. And today focused on to learning some kind of vectorizing in logistic regression in regard to gradient descent. So based on the M training example we follow below to get a derivative of z, which is equal to dz1, a1 minus y1. And it keeps to M training example in the same process. And by grouping all the individual dz's in a vector as a row vector, we can vectorize it. Also, we can vectorize it a and y. So we can substitute dzi with ai minus yi. And we saw this algorithm in previous sections to get a dw1 and dw2 and db. We followed these steps. The sum of the x1 I to times dzi. So basically, we just do some vectorizing here. So finally, we can optimize further our code by by removing the outer loop using Python's broadcasting. The broadcasting in Python follow the general principle is when the matrix n, when there is n by n matrix is A, with the operator plus, minus, and multiply and division with letters 1 by n matrix, the B becomes n by n matrix by copying its row n times. So, and professors gives us some Python and NumPy tips. Do not use rank one arrays because it doesn't represent any direction of a vector, whether it is column or a row vector. Instead of doing that, we better to use the um, this rand and with a rank, so we can identify whether it is column direction or row direction in this way. If we can't ensure that the shape of a variable, we can use a reshape operation to ensure that. And also we can use assert statement to check a dimension. This is optional and some kind of derivation how we get the cost function of logistic regression. So this is end of this today's record, and thanks for your watching. Bye.